welcome to lecture 3 of the second day of the Teachers as Scholars. I'm not sure why the camera is following me because the clicker is fixed on the ground, but so what I want to do now is I want to talk a little bit more about error correcting. So we've agreed that as a bare minimum, we want at least half of the message to be information and not redundant checks. And the question is how to do it. So I am not going to describe the best method. So a lot of the really good methods are due to hamming. I want to describe something that's almost as good, but much easier to describe. And we'll see that with a little bit of work, you can get something that is good enough to satisfy our requirements. So a lot of mathematics all comes down to how do you present things. If you present things in the right way, it's clear what you're doing. If you present it in a confusing way, you can go down the wrong path. And I showed the Rubik's Cube last time where if you turn it to 45 or 60 degrees, it's really the same as a 3x3 with patterns. But if you don't know to do that, it looks very different. So we talked about the tell me 3 times. And so the tell me 3 times majority rule. So tell me thrice, majority rule.
Oh, as an aside, I looked it up, and according to the Oxford Dictionary, there is nothing after thrice. So the word is not.
So we could actually invent
Twice.
double. So either double twice, or
How about twice?
or thrice. Twice. Twice. What is it?
I would do twice and twice.
Twice. Hi, twice.
QU with an
With an I.
I would be 5, I think.
Right.
Like
Quarce.
4 would be 4.
Well, this could be really good for Scrabble. Especially if you don't have the U. I mean, if you spell twice like this, oh boy, could you clean up in
If
Scrabble.
you have an H, you can do quiche.
I like that. Maybe 4 or 5 times.
So Philip K. Dick is a great science fiction author whose stories have led to numerous movies and TV series.
Who was his name?
Philip K. Dick. So I believe Terminator comes
Both
from
said it, so I still don't know what you said.
Philip K. Dick.
Um,
Terminator came
Blade
from
Runner.
Second Variety, I think.
Blade Runner.
Blade Runner, Do Androids Dream of Electric Sheep. The Man in the High Castle is The Man in the High Castle.
Scanner Darkly.
And then the other one is We Will Remember It For You Wholesale is Total Recall.
Oh.
So a lot of great stories from him. I can't remember if he did this one, but did you see the movie Minority Report with Tom Cruise? And this is one where you have 2 out of 3 agree, but the 2 ones that agree are agreeing for different reasons. And it's a very convoluted example of time travel and cognition and seeing the future and whatnot. So I want to show you another way to view the tell me 3 times the majority rule. I'm going to do it the following way. So black is always going to be data, and blue is check digits. So black equals data, and blue is the checks. So this is the standard way to view the tell me 3 times. Okay? Boom. I'm going to draw it in a different way. Because when I draw it this way, what's the natural generalization?
Then it's 3 zeros.
Well, no,
They're all the same.
well, no, I'm saying this is tell me 3 times. If you wanted to use 4 dots, it would be 1 black followed by 3 blues. 5 dots, 1 black followed by. So the generalizations here,
1 and minus 1.
right? And you can see that if you generalize it like this, you have less and less of your message being data, but you have more and more confidence of knowing what the correct data is.
Yes, that's true.
So you're trading, so it's a trade. In general, it's a bad trade. Right? But, but given that the Red Sox season begins tomorrow, we can all enumerate many bad trades the Red Sox have made over the years. I'm going to show you a different way to view this. I'm going to view it as 1 dot here, and then 2 dots like this. So when I look at it this way, here is a 1. In a marker of wonderful foreshadowing, we talked about check digits at the end of lecture 2. And you counted how many 1s were there in the row. And if it was an odd number of 1s, you write a 1 for the check digit. If it was an even number of 1s, you write a 0. So over here, if I want to transmit a 1, what should this be? So I put a 1 and I put a 0. How many 1s are there?
1.
1, 1, so I should put in a 1. And if I want to check down this way, what should it be?
1.
And here's another way of writing our message of 1. And if I wanted to send a 0, I would have a 0 here, and then this should be a 0, and that should be a 0.
Yep.
So my messages will still be 1, 1, 1, and 0, 0, 0. Imagine now we receive something other than a 1, 1, 1. Imagine we receive a 1, 0, 1 like this. Well, because this check digit is wrong, I know there's a mistake somewhere in this row. So the mistake is either in the first spot or the second spot. I don't know which, but I know error in the row. But now if I look at this one, this is correct. No error. So the column is okay. So if there's an error in the first row, but the first column is correct, the only spot where there can be an error is here.
Yep.
So this must be the mistake.
But how does this improve our engineering problem of having less of our transmission be made up of checks? We still have 2 checks.
Not at all.
Okay.
But maybe this will be able to generalize better.
Okay.
Drawing it like this rather than drawing it like this might suggest a better way of working with 4, 5, 6, or 7 points. So what I'm doing here is I'm using one thing to check the first row, one thing to check the first column. We're assuming that there's only one error. We're assuming that there's at most one error.
And this is a 1-digit message.
This is a 1-digit message. So we still have only 1/3 of the message is actually data. So it's still only 1/3. So it's bad in that sense. It's just a reformulation of what we've done before. So far, there's really no advantage in this. The advantage is if maybe this generalizes better. When we looked at it like this, the natural thing to do with 4 or 5 was to still just have one bit of data and then a bunch of checks. And that was a lot of checks. So the question is maybe we can be more efficient with how we use the checks. So if we had an error here, let's say that this was the message that was received. Now we know that there has to be an error in the first row. We know there has to be an error here. And given that we're assuming there's at most one error, if there's an error here and an error here, this has to be the error, and now we can correct that. And if you look at this, this really seems a lot like if you see two things that are of the same and you're the opposite.
Yeah, the hat problem.
It's the hat problem. Okay, so now this would allow us to transmit 1 digit of data. And it costs us 2 checks. What if I wanted to try to transmit 2 digits of data? Well, I could try to play the game as before. I could put a check digit here. And I could put a check digit here. So let's see if this would work. I'm sorry? So I'm missing the second column. So if this is wrong, then I know there's a mistake in here. If this is wrong, I know there's a mistake in here. That will uniquely determine here. If this is right and this is wrong, I know the error is here. But unfortunately, if this is wrong and this is right, then I just know one of these two is wrong. And it doesn't help. So what I would have to do is do it like this. And
So now we're at 2/5.
so I now added,
You're at 2/5.
right, so basically I added 1 bit of data and 1 check. So now, at 2/5 data.
So now we're at 0.4 instead of 0.3.
Right. It's an improvement.
Definitely.
Okay? And that's much better than the other way we did, which would have been over here, if we did it like this, that would have been 25%. We'd be going down. This is going up.
So in theory, you could extend that out to more points, 2 data points.
Right, so the question is, how does it look as we keep extending? So is everybody comfortable that this will catch 1 error?
Sure.
So let's do like one example. So imagine we have 0, 1, 1, 0, 1. Hopefully this is right. So this is wrong, so that's too many wrongs.
No, those are right.
correct.
Right. so
This one's
now
correct.
you have no error.
That one's not correct.
Right,
That should be a
I
zero
want to
there.
have one error.
Right.
But when I had a 0 here, I had 2 errors.
Yeah.
Yeah, because
Yeah.
if this is a 0,
Then you
this
got
should,
two
this
errors.
should be, do I have an even or an odd number of 1s? I only have 1 1 here, so this should be a 1.
Right.
Oh, I thought it was a check for the sum of all the black.
No, it's a check for the blacks just in this column.
Oh, I'm sorry.
That's fine.
I thought it was the
Yep.
sum.
Nope.
I thought that check digit was the sum that we did earlier.
Right, it's for that column.
Okay.
So this is the check digit for the second column, this is the check digit for the first column, this is the check digit for the first row. That's why I wanted to do an example.
Okay.
So now if I make this a 0, I will see
Yeah.
that this is wrong, and I would see that this is wrong, and I would see that this is, so I've got
So
2
with the
errors.
row, though, it's the sum.
I'm sorry? For the row, it would be the sum.
Okay.
So there's an asymmetry here because we have 2 data points. So if I do it like this, I know that this is correct, I know this is correct, and I know that there's a mistake over here. Well, the mistake can't be here because I know this row is correct. So this must be the error right there. Conversely, if I make this a 0, and I make this a 0, then I know this is right, and I now know that there's an error here, and this row is correct, so the error has to be here. If I now turn this to a 0, I now know there's a mistake in the first row. There's no mistake in the first column, but there's a mistake in the second column. It has to be here that's the mistake.
And then as you extend this, you would be improving your data transmission percentage as you get the message bigger and
Right.
bigger, right?
So for instance, one extension now, so we could do maybe 1, 2, 3, 1, 2, 3, and 1.
Right.
And that will work.
And now you're at 3 7.
And now we're at 3 7ths. So we then get to,
So this is one of those rare examples where scaling up actually makes it even more efficient.
it makes it even more efficient.
Yeah.
And in the limit, we can get up to
You're right, it's not scaling. You know,
n divided by 2n plus 1. So we can get to almost 50%. So I was extremely careful at the end of the first part of today's lecture to make sure that I said I want at least 50% to be considered a success.
And that was $49.99.
And so this,
That's the
exactly,
answer, yeah.
yes. Rounds up to 50%, but it's not 50%. So less than half your message is information. So this will be considered a failure.
Okay.
But, you know, it's not as bad of a
Definitely
failure as the other.
improvement, yeah.
It's an improved failure.
And it also,
It hinges on having more pieces of information doesn't increase the likelihood of having more than one error.
Well, but it will. Because if you made the message far too long, then you would definitely have a chance of 2 errors.
but this also allows you to identify where the error is specifically.
This allows you to identify and correct the error.
Yeah.
So we were talking about when we did the tell me 3 times majority rule. If we write it as a straight line, if we want to generalize, we just keep going further and further and further. But only 1 bit is going to be information. If we start arranging things differently, we can actually have more of the message being data. So one possibility was if we did it in a pattern like this, the blues are always the check digits. And so this would be, is there an even or an odd number of 1s in the first row? Well, the first row is just here. Is this an even or an odd number of 1s in the first column? It's just here. So if this was a 1, then both of these should be a 1. And if we receive this as a 0, then we know there's an error in the first column. But the first row is correct, so that means the error must be here. If we got 2 zeros like this, we know there's an error in the first row, and there's an error in the first column, so the error must now be here. And then we saw that we could extend it by putting in more black data points, and just each column having a data check. We can get it so that we can get 2 5ths, 3 7ths, and in general, just a little bit less than 50%.
Would it be helpful to have the data points in more of an array than
Ah, so that's a great question. So maybe we shouldn't be doing a straight line. But we don't have to visualize it. We just need ways to refer to things. So with 2 points determine a line.
Yeah.
Unless you're in marketing, in which case 1 point determines a line, and you just ask your boss, what does your boss want to see?
And 3 points determine plane.
3 points, 2 minute plane. So with 3 points, we actually have a freedom of how to place them. So for 2 points, I really have to put them in a line. For 3 points, how would you like to place 3 points?
Put them in a L.
I was gonna say triangle.
Okay, so let's put them in a triangle. So we can start thinking about how we might want to now put the check digits. So I could have a check digit for the first row, which would be over here.
Yeah.
I could have a check digit for this diagonal here, and a check digit for this one up
And you're
here.
automatically 50%.
And now that's going to be 50%. So if I arrange it like this, this is a check digit for these two, this is a check digit for these two, this is a check digit for these two. So if I give you the message, 1, 0, 1, this should be a 1, this should be a 1, and this should be a 0. Imagine now I receive 1, 0, 0. This check digit tells me there is a mistake in this row. So one of these two is wrong. This is correct, so this one isn't wrong. This one is wrong, so it focuses, this must be the error. So this now gets us 50%. So we've now hit 50%. And the cost isn't that much more.
I don't really see it any more cost.
Well, we have to transmit 6 digits as a whole thing.
Okay.
So you are more likely to have 2 errors in 6 digits. But if the probability of an error is sufficiently small, I'm not that worried about transmitting things in blocks of 6. And now half of my message is information. So the question now is, this is the solution when we have 3 bits of data to transmit. If you had 4 bits of data, how might you arrange 4 bits of data? 2 by 2 array. And in fact, the 2 by 2 array is going to be much easier to write. Here, I've basically got this kind of...
And it allows you to work in just tables in rows and columns.
yes. So now, I would do it like this. So if my message is 1, 0, 1, 1, this should be a 1, this should be a 0, this should be a 1, and this should be a 1.
Okay, so you're not.
Did I make a mistake? Oh no, this should be a 0.
You're not checking the 2 diagonals.
I don't need to. If this one is wrong, there's a mistake in the first row. If this is wrong, the mistake has to be here. If this is wrong, the mistake has to be here. If both of these are right, it's the check digit that's wrong. So if I receive this message, I know there's a mistake in this row. This one is correct, this one is correct, this one is correct. So this is right, this has to be wrong.
The other part of this is it's self-correcting so that you can correct it.
Exactly,
Yeah, so you don't
exactly.
have to resend it.
Exactly. So I can correct either the check digit, which I don't care about, but I need to know where the error is. Or if the actual data is wrong, so if this was a 1, let's imagine we incorrectly received this. So now, there'd be a mistake in this row. This would still be correct, this would be wrong now, and this would be correct.
So where's the error in that example?
So the error, it's somewhere in this column, it's somewhere in this row. The only intersection is this one here.
Okay, gotcha.
So this is the error. So what's the transmission rate here? What % is data?
4 7.
Nope.
Or eights.
40. Oh, 17.
Or black.
Question?
I was just wondering, is the 0 a digit or is it?
Yes.
This,
The black ones
You're
are
using
white.
circles.
the black ones are the data that we want to transmit, and the blue ones are the check digits. So we're sending 8 numbers.
So the check digits are redundant, so I
Well,
want to make sure we.
so at the end of the day, we will throw away the blues, and we will only care about the blacks.
Yeah.
Blues are helping us find.
But
the
blues are
difference.
helping us find where the blacks transmitted correctly.
I'm using redundant as engineering, meaning not as a disparaging term.
Okay, as you learned from the Department of Redundancy Department?
Well, no, like in engineering, redundancy is of course building an
Yes.
additional safeguard.
Correct. And so here, at the end of the day, once we confirm what the message was, we only care about these 4 bits here. But we have to transmit 8 bits to be confident about these 4. And if there's a mistake made in any of these 8 bits, as long as it's just one mistake, we can correct. So we have 2 different schemes, and both of them
Give us half.
give us 50%. Yes.
But how do you know how to construct the message from that grid? I mean, is there convention that you do rows and columns?
Well, you just decide. So for instance, I could have this as maybe D1, D2, D3, D4, D5, D6, D7, D8. It doesn't really matter what rule I use as long as I'm explicit and clear. And if I do this is my rule, then I know the first things over here is my message. And I would read it as D1, D2, D3, D4. So which method is better, the triangle or the square?
They're the same.
I gotta go with the square.
Okay.
Because
Well, let's have a show of hands. How many people prefer the square? We've got 1, 2.
I have,
I'll be honest with you, my bias towards spreadsheets is making
Okay.
it works
do
in
that.
So the square seems to be beating the triangle.
Manually, yeah.
How many people prefer the triangle?
I want to see a bigger one.
Wait, can I change my vote?
Yeah, I was wondering how many people are going to change their vote.
So would it depend upon how much data you're transmitting? Like, I feel like it would just be basically a regular end-on, depending on whatever end you're
Right.
transmitting and piece of data.
But there's a reason why the triangle is better.
We're not looking at larger arrays, though. We need to look at triangular array and a
Yeah, let's
square
look at
array.
one like,
See which one needs more check digits, right?
Well, so in both of them, we have a 50%
right.
messages data.
Yeah.
So if your criteria for success is which has a higher fraction of data being transmitted, it's a tie.
Yeah.
So now we need another criteria to split the tie.
How they're gonna fit together in the.
Well, but so mathematically, I can just still write this as D1, D2, D3 if I want, D4, D5, D6. I can easily program the computer to handle this. The computer doesn't care. I know for humans, putting it in a nice grid like this is nice, but the computer can easily handle something like this. There is a reason why the triangle is better.
Oh,
It's checking all the pairs.
I'm sorry?
It's checking all the pairs.
But I don't need to check all the pairs here.
Yeah, you threw that out.
So if I check this pair over here, it's redundant.
Right.
So why is it better?
the triangle?
Triangular.
He said the triangle's better, but I don't
Triangle's
know.
better.
You to base 3?
I don't know.
So
I mean, the only reason like you said, like the tables are better for humans, and I'm thinking about databases and things like that, and I'm like, tables and rows, right?
Okay. So right now, how many bits of data do I have to transmit here?
6.
6. And how many here?
8.
The more you transmit, the more likely you are to have 2 errors. So here, I can get the 50% using a smaller number.
But if your message is 4 digits long.
Yeah, your message is smaller too.
Well, I just do this every 3 digits. Every 3 digits, I just do it like this.
Oh, that makes sense.
So if I wanted to do a very long message,
Oh,
I
so
break it up into
all the
blocks of 3 or
messages would
4.
be packaged into 3 or 4
Into
bit
3 or 4 bits.
packets.
Right. And then those 3 or 4 bits you transmit using something like this.
Okay, then you can make the triangle better.
So the triangle is a little bit better because you have less of a chance of 2 errors. You still have the same efficiency, but you have a less of a chance of 2 errors because you have fewer things.
Well, then it definitely wins.
So this is 3 versus 4. Is this a success?
By your criteria, yes.
So by the weak version of Miller's criterion, I want at least 50% it's a success.
So you're squeaking through.
So we're squeaking through. I mean, this is like, the student who does the bare minimum to get
It's gonna be
by.
on the test.
Hey, it doesn't
And
matter
my
if the ball
response
plays
is,
the
it is on the
by
test
an
now.
inch or a yard. A home run's a home run.
A home run is a home run. But so for some things, it doesn't matter if you just barely squeak by. My wife had a friend who wanted to be the hardest tenure case in their school's history, requiring days of deliberation before they just barely are granted tenure, because then they will know that they have spent exactly the right amount of time on their professional career. It is a very dangerous calculation, because if you just miss,
That's an
I-
interesting thing to do.
I taught at Brown for 4 years. Brown does not have pluses and minuses in the grades. So if you just miss the A minus, you get a B. But if you just get above the B plus, you have an A.
Yeah, I remember talking.
So this barely squeaks by, but I'm not excited about this. I want to break 50%. So we've done 3 bits of data, we've done 4 bits of data. What should we try next? So one is to try 5. Is there a good pattern for 5? How might you try to do 5? So if I try a pentagon. So 1, 2, 3, 4, 5. Unfortunately, if we do every 2, how many check digits will that be if we do every 2? Okay, so I'm sorry. So if we do every 2 consecutive, that would be 1, 2, 3, 4, 5. So if we do it like this will work.
And if you do 2 non-consecutive, it's still 5.
And exactly. And if you do 2 non-consecutive, you'll have trouble because this would go with this one would go with this,
Yep.
this one would go with this one.
There's 5.
It would be 5. You'd be okay, but you'd still be in trouble because it's only 50%.
If you did it like a 5 spot, I think it's 1, 2, 3, 6. Did it like
So
spot
this is
like
where you
that.
draw 2 lines.
Well, what if you did 6 as a table instead of 5?
So one question is maybe 5 is a bad number too.
Yeah, that's what I was just thinking. Maybe.
So here we go. So let's form a table here. Number of data, and then we'll do
Number of checks.
checks. Yeah.
Or percentage.
or percent of message. So we saw when we had 1 bit of data, it was a third. We saw when we had 2 bits of data, we got up to
49.99.
2 bits.
no, it was 2 bits.
Yeah.
But then when we had 3 bits of data, we got to 50%.
Right.
So I'll switch to percentages. And when we had 4 bits of data, we also had 50%. And right now with 5 bits of data, it's looking like it's still 50%. That I don't see a better way with 5 bits of data.
No. I see.
Maybe there's a better way with 6 pieces of data. And so what I like about this is, again, what math am I using? I'm using algebra and some really basic geometry. So this is math that you can do, I think, early in students' careers. It now comes down to what's a good shape to try. So we have 6 pieces of data. How should I stack them? I'm sorry?
Rows of 3.
So 2 rows of 3? All right, so let's try that. Oh. So we have 2 possibilities. A triangle with 1, 2, 3, or like this.
Yes.
So let's
Maybe
just,
the tables and rows. Guys.
so let's see what this is. Okay? And again, one of the things I love is when you have a problem that has an optimal answer, as well as answers that are better than what you were doing. And for so many things in life, you don't have to jump immediately to the optimal. If you can just do better than what's being done. And I have made a very good career as a consultant by doing just better than what is being done. So let's see what we would have here. We would need 1 check digit there, 1 check digit here, and a check digit here, here, and here. So do you agree that this will work? If there's a mistake here and here, it's in this row and this column, uniquely identified. If there's just a mistake here, it's just in this, must be here. All right, so what would you get with this? 6 11s. So what we've just shown is that if we do 6, we can get at least 6 11s.
64%. More than 50%.
So we've at least won. It's now a clear victory. It may not be the best you can do, but you've at least broken 50%. You can actually break 50% with 4 bits of data and 3 check digits. So there's actually a way to do 4 pieces of data and 3 check digits. We were using 4 check digits. That was Hamming's genius, is he found a way to transmit
3D.
4. Not 3D, it was related to base 2. Hamming. So I will be sending links on this. So these are called Hamming codes. And you can generalize all this stuff to detect 2 errors and stuff like that. Okay. So you're in the running right now, you're in first place. But there was a suggestion that we try a triangle
I
pattern.
was going to ask you what would happen if we did this.
And the reason why I'm erasing what you're doing. I think the triangle is going to do better. So let me see if I can remember how to do it, though.
With 6 are you talking?
With 6. The problem is drawing it is not easy. So let's see. One is we could do a check digit here. We could do a check digit here. We could do a check digit here. Now, if you look, how many times has this one been hit? This one. This one. These three haven't been hit twice. So what I'm going to do is I'm going to have another check digit that goes through those three.
So they're all hit twice.
So everything is now hit twice. So if two check digits are wrong, that's going to uniquely determine a point here. Because each point here is on exactly two of these generalized lines. And so
we could visualize the data as the 6 edges of a tetrahedron, and the check digits are the vertices.
if you view it like three-dimensionally,
Yeah.
That work?
Yeah.
I think that would work.
Six and more, yeah.
So we'd have 1, 2.
Or the faces. Maybe that's
So wait a minute, for the tetrahedron,
Right, it's touching.
four faces.
6
four
edges,
vertices.
4 vertices, 4 faces.
Right, so it could be the faces too, the four.
Yeah, it's on dual.
Yeah, right, some dual.
so would you have like an equal out triangle here, then a point up above, a point below, and look at the faces
No, just 1 point,
above?
yeah,
So like this?
kinda, yeah.
Okay.
There's six, you just drew 6 line segments.
Oh, okay.
That represents your 6 pieces of data, and your 4 dots are.
Oh, your four checks. Yes,
Yeah.
yes. So this is another way to draw it.
Yeah,
So we now have 6 pieces of data and only 4 checks. So that would get us 6/10, which is better than 6/11. Now it's a shame that Brett left, because we can redo this and we could ask, well, what if we had 7 pieces of data, 8 pieces of data? What do you think would be another good number of data to have? So 7 and 8 aren't great numbers.
triangular numbers.
So triangle numbers are nice. So 1,
10.
10. So another triangle number could be nice. What else might be nice? Okay. Brett is back now.
What's been nice so far?
Well, what is Brett like?
Brett likes square array.
Brett likes square arrays. So what number would be good?
Even number.
Not 8, 9. So if we did 9, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah,
So if you did it to tetrahedron, so it gets you 6/10.
nice.
So you lose, but not by much. So you were competitive. And now we've turned it into a square array. So if we do 9, we've got 3 here, 3 here.
And of course, square numbers are better for the same reason.
For visualizing.
But squares have more area, let's say, than a rect, or can less perimeter.
Yes.
Well, what fraction of our message?
9/15.
9/15, which is?
I got it.
3/5.
Yeah. Duh.
Again.
Well, after I gave a
It's
lecture
math.
that 12 24ths is 1/4, I don't blame people for having some concerns about
Let's
algebra.
show you that for later, Brett.
What?
The fraction thing you did earlier.
Yeah.
Okay. I should show that one.
So these two are both going to be 60%. Which is better?
That's big.
The one with less points to transmit.
Right.
Although this is much easier for me to visualize in code, I can still do this, and it's worth spending a little bit of time writing a line of code to be able to use fewer pieces of data. So how many pieces of data does this use? 6, 10? This uses 10 pieces of data, right?
For 6.
So this is 10 pieces of data.
Well, we're just looking at the
No,
overall
10
transmission.
transmissions for 6 pieces of data.
Oh, I'm sorry, it transmits 10 bits.
10 bits.
10
for
bits.
6 pieces of data.
And this is how many bits?
15.
15 bits. So you can see now,
9 bits of
That's a
data.
big difference between before it was only 1.
It's a 50% increase in overall transmission.
right, but of course you get 9 digits at once, whereas here you only get 6.
Yeah, still 50%.
But again, you have more of a chance of a double error with something like this.
Right.
So what you could do is you could ask, well, let me keep expanding this. And I will leave this as exercises. You can look at all the triangle numbers. So the next one would be 10, then 15. and look at all the square numbers. Is each triangle number equivalent to each square number in terms of efficiency? How do you start drawing like the tetrahedron and these lines? Can you continue to do this? Are there better shapes to use? What if you expand to higher
I was
dimensions?
going to say, what if you did a sphere? Because spheres have the best ratio of volume to surface area.
Right, but you've got to be able to align things.
Yeah, that's true.
So,
Sure there's a way we can make that happen.
so I like just a little bit more. So let's imagine we wanted to do say something like this. All right, so we've got 8 bits of data arranged as a cube. How do we want to transmit check digits? I could do a check digit for each row and each
What if you
column.
did diagonals?
There's a lot of things. What if I did one for each plane? A check digit for the top plane, a check digit for the bottom plane, a check digit for the far left and the far right, a check digit for the back and the front. So that would be 6 check digits, I think. And if this one and this one was wrong, it's something in this plane on the back, this plane on the top.
So we only narrowed down to 2.
I've narrowed it down to 2. Is this going to be enough to uniquely define? It should, because I've also got the back one. So I know if the back one is correct. So let's say this one is wrong. So I know that there's an error in the top. So I know one of these is wrong because there's an error here. If this one is wrong, then I know there's an error in one of these back 4. So now I know it's either this one or this one that's wrong. And now I look at the check digit for the back.
And it's right.
And that one, let's say that one was correct, and the one for the front was wrong. Now I know this has to be the one that's wrong. And because of all these check digits, each one of these should be in exactly 3 planes.
What if you had a double error?
We don't have double errors. We're always assuming we don't have double errors.
Okay.
So you can go through, and I believe this will work. So we have 8 bits of data. Do this in black. And how many check digits? 6.
Yeah.
So this is 8/14. So this would be 8 bits of data. All right, so 8/14 is the same as 4/7?
It's 57% roughly.
Happy or not happy?
We're not as good as what we had.
Not as good as what we had. So does this mean 3 dimensions is worse than 2 dimensions?
No.
What should we try next?
Tesseract.
No!
I'm trying to think here.
I'm not a witch. Nope.
Icosahedron.
Nope. Keep the shape simple. What should we try next? No. Keep the shape simple. We tried the 2 by 2 by 2 cube, right? And it didn't work. What should we try now? 3 by 3 by 3. Maybe it's just a case of small dimension and small size. Remember, we saw some things you didn't get the savings until it got larger. Maybe if we made things larger, it would be a little bit better. So let's look at what the costs would be. So, this is going to be really bad drawing. So here is, the first one. And then down here we'll have the next one. So, here are my layers. And then the last one. So we now have 27 bits of data. And now let's think about how many planes we need. We have 3 horizontal planes, right? We have 3 vertical planes and 3 front and back planes. So how many planes do we have total? 9. So 9 check digits. All right, 27 over 27 plus 9, that should be 3/4. So now, while 8 failed miserably, 9 is pretty good. So this actually was transmitting 27 bits of data at a 75%.
So it seems to be that multiples of 3 are the key there.
Well, we could then do 4 by 4 by we could do 4 levels of 4 by 4 planes, and that would be even better. If you think about it, if you have n by n by n, you have n cubed data. And now let's see, how many planes do you have? But that's the question, is it a and this is the problem with small data. Right. We'll have n. Well, if you look at how many planes are like parallel to the xy axis, there should be n planes parallel to the xy axis.
So n to the third.
Not into the third.
3n.
It should be 3n.
Right.
There are 3
Oh,
planes
3n,
parallel
3n,
to the xy
sorry,
axis.
3n, yeah.
There are 3 planes parallel to the yz axis, and there are 3 planes parallel to the xz axis. So you should have 3n of check. And so n cubed is going much, much faster than 3n as n gets big. So if we check, so what we'll do is we'll make a little table. Here's n, here's data, and here's the checks. So when n was 2, we had 2 by 2, so it was going to be 8 bits of data. And the check digits was 6. And 6 is equal to 3 times n. When n equaled 3, we had 27, and we had 9. So again, sometimes it's hard to see what the formula is with small values as to which way it goes. But we have a linear cost in check digits versus a cubic growth in data. The problem is these messages are now becoming bigger and bigger. And so the probability of having 2 errors is now getting larger. And as this gets very large, and then the question is, can you do something better than a cube? Would a tetrahedron or some shape like that allow you to have the same efficiency with a smaller size? So there's a lot of great questions you can give students along these lines. And I'll be giving some high school students questions related to this. What I like is this is not the optimal way to do things, but you can get so much better than the majority rules and the simple stuff so easily that to me it's worth doing. And sometimes it's not worth going to the ultimate answer. So I will send you a link to Hammond's code as to how you can use 7 bits of data to transmit 7 bits and have 4 of them data and only 3 of them checks. So there's a way to do that. Yes?
Well, I'm handicapped by ignorance, in case you haven't already noticed. But, so when I'm thinking, you're sending a lot of data, right? I'm
Yes.
thinking about the codes where you're breaking it up.
Correct. We're breaking it up into pieces. Yes.
So if you're breaking up this data, doesn't the shape of it have something to do with the efficiency? So when I'm looking at the 6 that is arranged in a triangle, and you have that loopy check like that,
But I'm saying the computer can just code that.
the
So,
computer can do that.
so for instance, if I'm sending D1, D2, D3, D4, D5, D6, so I'm sending a string of 6 things. The last 3 are going to be check digits. So I'll write them in blue. D4, D5, D6. And so what happens is I start off with my message, D1, D2, D3. And then I'll make this one D4, I'll make this D5, and I'll make this D6. And so for D4, I'm going to send this basically D1 plus D2 mod 2. And D5, I'll send D2 plus D3 mod 2. And D6, I'll send D1 plus D3 mod 2. So you give me D1, D2, D3, it's very easy for me to choose the string. And then the computer knows if I have an error in D4 and D2, where's the mistake? If I have an error in D1 and D, et cetera, et cetera. So if it sees an error in D5 and D6, the only thing in both D5 and D6 is D3. So if those check digits are causing an error.
You must have more of your riddle based on some of these ideas. I mean, you had the Pentagon riddle for us, where can we introduce 2 lines and get 10 triangles?
That's completely unrelated.
It's not.
It's not. At least I don't see the relation, because that's cutting a pentagram and forming shapes. That's one of the riddles that has the most wrong answers submitted. So for those of you who haven't seen the riddle,
That seems totally related when we put Pentagon up there.
so you start off with a pentagram like this, and it has 5 triangles, 1, 2, 3, 4, 5. You want to draw 2 lines, and somehow, depending on how you draw the 2 lines, you want to have exactly 10 triangles. And there is a way to do this. So this would give me 1, 2, 3, 4, 5. This is not a triangle, that's quadrilateral. 6, 7. And these are not triangles. So it is amazing how many people send me wrong answers to this. And I yell at them and say, look, there's no way you should send me a wrong answer to this. You cannot know how to do it, that's fine. But you have to just count to 10.
Check your work.
And is this a triangle or is this a quadrilateral? How many sides does it? This is easy to check. So there are some things in math that are very hard to find, but they're very easy to tell if you have the right answer. So for instance, factorization. Right now we believe it's hard to factor a number, but it's very easy to check and see if somebody has the correct factorization. What do? Multiply. Right? It's not that hard. So a lot of these problems are based on schemes that are thought to be hard in one direction, but they're easy to verify. And as long as you can verify easily, there's often graph theory problems. Can you come up with a tour that goes through each city exactly once? And you can only use each road at most once. Well, it's very easy to verify if a proposed path works. Just check and see, did you go through every city exactly once? Did you ever go on a road twice? Done.
So when you're talking about the triangle and the pentagon and the cube,
Yes.
that's just a way to visualize.
It's just a way to visualize.
And then the computer has a linear string.
Right.
Okay.
A computer does everything with the linear string. But in terms of trying to visualize what we're doing. And the whole idea is, what I love about this problem, and I will see how well it works with 4th to 6th graders. I've done a little bit of it. The students actually did discover the triangle. Is you start off with a simple answer, and then you start asking, what other shapes can you try? And you start, we have blinders on, and the first thing is when you do tell me 3 times, or tell me 4 times, tell me 5 times, you keep that straight line. Once you smash the idea of looking at a straight line, and we have the idea of looking at a triangle for 3, and also maybe a square for 4, then the next natural thing to try is a pentagon, and then we see, the pentagon doesn't work. And then for 6, we see that there's 2 ways to do it. We could do 2 by 3, or we could do a 1, 2, 3 triangle. And we see they give different answers. So we see how we put them together helps. And we want to be as efficient as possible. Every time we do a check, that's expensive. So when you did it as 2 by 3, well, some things were checking 3, and some things were only checking 2. When we did it as the tetrahedron, then everything was checking 3 things, and it was more efficient. So going up to 3 dimensions became really efficient. And you might think, is it worth a 75% success rate to do this? Well, no, because there are better ways of doing this using a smaller number of vertices. Okay, any other questions on this? All right, I will end with just one bit on cryptography. This will probably not record. So let's see if we can project. So it was on earlier. Let's see. So this is the idea of hiding images in images. So this is a cute application. Okay. So it's a little bit odd.
Very good.
Art. So does everybody see the tree?
I see something that could be a tree.
A symmetry.
Oh, clever.
No, but it's not going to show up because I'm using the graphic recording, so the people at home won't see it all. There's a cat hidden in the tree.
Okay.
Does anybody see the hidden cat? I'll save you time. The answer is no, no one sees it.
No, I don't see.
Oh, and besides things wrong. So here is the hidden cat. So the question is, how is the cat hidden in the tree? So if I want to send a picture, what I can do is I can split the picture up into cells. And for each cell, I send a red, green, blue triple. And we normally have these numbers range from 0 to 255. Anybody know why 250? Yes.
Can you go back to what was a red, green, blue?
So when you send an image, the way you often store an image is you break the image up into a bunch of small cells. And for each cell, you have a triple of red, green, blue. And then that will give you a different color for that square. So it's pixels.
So it's some mix of those.
It's some mix of those three. So, you know, you can have from strong green to light green. And so are these the primary colors?
Oh, I
No.
know it. No, they're not, but that's just what they use.
This is what they use, but
Yeah,
it's the
I don't know why.
complement to the primary.
It has something to do with the fact that the way you can mix them and stuff.
Right.
I don't get it. You'd have to be a physicist to know that.
I'm sorry?
Why 255?
So what's nice about the number? How many numbers are there from 0 to 255?
256.
Two, the whatever.
Yeah. 2, 4, 8, 16, 32, 64, 128, 256. 256
It's a byte.
Yeah.
is 2 to the 8. So basically each number is an 8 tuple.
Or a byte.
Which is why in Photoshop a lot of settings are from 0 to 255.
So we would have it as, you know, so let's say 7, 6, 5, 4, 3, 2, 1, 0.
Is altered.
So we can visualize it as a cube
And
in
you go
terms
heels,
of
you can transform.
how much R, G, and B
Right.
dimensions.
So over here, if you give me a number, say you give me, 177. That's equal to 1 times 128. I'm going to have 0 64s, right? I'm going to have 1 32nd, so there'll be 1 50, that'll be 160.
A 16 and a 1.
A 16 and a 1. Okay. And so the tuple here, I would have no 256, 128, no 64s, 132, 116, no 8s, no 4s, no 2s, and a 1.
Call it a byte.
Oh, no, there's no 256, right? Be like this. So that would be the string corresponding to this value of red.
And that's just the red number.
And that's just the red number. And then I would have the green number, right.
Two more numbers.
So I have 2 more numbers. So imagine this is my number. If I change the last bit from a 1 to a 0 to 1, is it going to change my red intensity by that much?
No.
What if I change the last 2 numbers? Is it going to change my intensity by much?
Yeah, that might be noticeable.
1 by 3.
I mean,
3 out of 255, that's not much.
It's not going to be a huge amount. But
maybe not.
let's just change just the last bit. So what I do is I throw away my last bit, and I take another picture, and I'll do this picture in black and white. And so I'll let the last bit be a 1 if it's a black pixel, and a 0 if it's a white pixel.
Okay.
And so now I transmit this new message. So the last digit could be wrong, but hopefully it's only wrong about half the time. So half the time, I'm actually going to still have the correct bit here. Half the time I'll have the wrong bit. And now if I just pull off just the last digit as 1s and 0s, I can read off my message. So I can take another picture, a low resolution picture, and hide it in a high resolution picture.
I have the
Okay, so let me try again. So imagine you have two pictures.
Okay.
This picture is just in black and white. So each pixel is going to be either a 1 or a 0.
Is that the picture that we want to encrypt?
That's the picture we want to hide.
Okay.
I now take my regular picture
Okay.
and I look at the last digit of the reds.
Oh,
I leave green alone, I leave blue alone, I'm only going to change red.
okay.
And I'm going to take the last digit here, and if the digit here is a 1, I'll make it a 1.
In that one picture?
In that one, not in the one pixel, in the one digit of one pixel.
Okay.
So I'm only changing the last bit.
Of one pixel, and you're putting the, whatever it is in the black and white picture.
Correct.
As the digit of that.
Correct. And so now, when I receive the message, when I receive the picture, it's going to be very hard to notice that the picture's been modified.
Sure.
Because half the time there's going to be no mistake here.
But if I can filter out all the other digits.
Right.
just
If you
look-
just look at just the last digit of the reds,
We're talking about, you gotta know to look at it.
you have to know to look at it that way.
Yeah.
And that's how we were able to hide the cat in the tree.
Oh my god.
So basically what you're doing is you're using the numerical value at the end of the red pixels in this
Right.
example
And what you
to
might
set
notice
the
is
value of the
cat here is
picture
not
that you're encrypting.
nearly as sharp as the tree
Yeah.
is. Partly it's screen projection issues. But it's, the fewer digits you have here, the fewer choices you have of color. If I have two digits, I can either do 0, 0, 1, 1, 0, or 1, 1. I can represent four things. So I can be 0% of the way down, 25% of the way down, 50% of the way down, 3/4 of the way down.
So how far can you push it?
Well, the more digits you use here, the better picture you can have, but then the more noticeable degradation you're going to have.
And that picture
This
won't
is not
look good.
black and white, so you.
Right. So here, this is maybe using 2 or 3 digits.
So the higher the resolution on the picture you're using as the mask, the better
Exactly.
you can
So if instead of
render your
using
own.
256, if I went even further here, then I could have more digits here that I could change without anything being noticeable. And then the other thing you could do is, instead of having just 1, 0 and have the message, you could have some kind of encryption scheme here.
Yep.
So that if somebody that knows how to decrypt it, maybe what you do
Still
is,
encrypted, yeah.
you
Or
know,
still encrypted, yeah.
you multiply it by the square of I plus j words in the ijth position, or something like that. And if you do have something like that, you put in a little bit of randomness, and then when somebody just quickly looks at it, they won't see the message.
Now, Steven, is that something we could do by hand, kind of simply to give kids like a simple example of
Oh,
what
man,
happened
that would be
over
tough.
here, or no?
Well, what you would have to do is you would have to have the RGB values for every cell of a picture.
Yeah.
So if you can do this in Excel,
Yeah.
you would then have to just look at the last digit.
Okay.
I have an activity I do with my 8th graders that teaches them about transmitting pixels and rendering
yeah?
images. It doesn't even touch encryption.
Right.
Just based on my experience, I think that would be really difficult
Okay,
to do
okay.
with them.
But what
I mean,
you-
even what I'm doing, they can barely.
Yeah.
But if you had a program, and I can see if any of my students want to write the code to do this, where you just take the pixel and then just change the last value based on what you want to come over here, then you
Yeah.
could actually see the message being hidden. There might be programs online that do
There's
this.
probably some sort of simulator somewhere.
Okay.
I wouldn't be
Yeah, that's a good
surprised if
point.
something is online.
Yeah.
But what this means is it's very easy for you to hide a message. So if
Yeah.
you just transmit something in black and white, you could actually take a letter, scan the letter, and then embed that in the image.
Mhm.
And so if there's a terrorist cell, you can actually put a message like this. So some of the work I do is related to detecting when has an image been modified. And so there are tests you can do. I would prefer not to say anything about this with the camera rolling. This is like the really bad question on 912 to the pilot. Are there any secret ways of alerting people on the ground terrorists might not know about?
Why is it only 50% of the time it would be different? And
Well, what I would say is just the odds are that half the time maybe this digit should match that digit.
Why is there a little tilde over there?
Oh, because I'm saying originally it was R0. And then I'm replacing R0 with whatever I should have had from here. So I'm now changing the picture just a little bit. And again, percentage-wise, you're talking about at most 1 out of 256. That's not going to be a significant change. And you would even expect half the time it shouldn't be a change at all. Either maybe half the time they line up. So it's very easy to embed an image like, the computer programs can run through this without any trouble. The difficulty is knowing when to check for something like this, and what kind of more complicated schemes can you do.
Right, because if you still have your encrypted message with another level of encryption, that only gets you part of the way there. And I'm sure that's what a lot of people would do.
Right, absolutely.
And if you use a one-time key, you'd have no way of breaking it.
Right, but you want something that anybody who you want to receive the message can easily receive the message. All right, so I think this is a good time to break for cookies.